this week's topic is Hubble's Law. So hopefully you remember that we looked at the distance ladder and how we measure the distance to distant galaxies and galaxy clusters. And so we've got distances using things like the Tully-Fisher relation and Cepheids and supernovae out to a very long distance. And so here's the map of how we do that. So for things that are at megaparsec distances, we can use the Cepheids, the Tully-Fisher, and the supernova method. And then we can look at some of the properties of the galaxies at those distances. So if we look at those galaxies, we find that they're redshifted. That is to say that if we have, say, a hydrogen line in the rest frame, instead of being at 650 nanometers, it's redshifted out to more like 800 or even 900. And we can use that to work out its movement away from us. How fast is it moving away from us? What Hubble did was to notice the relationship between the recessional velocity, it's always redshifted, it's always moving away from us, and to start with, just 5 galaxies. So we had these 5 galaxies that had known distances because they had Cepheids or Tully-Fisher or whatever, and the Doppler effect gave us the recessional velocity. And you can see it's a fairly nice straight line. As he added more data points, he looked at more galaxies, he found that they continued on this same trend. And so this is where Hubble's law came from. And Hubble's law is just the equation of that straight line fitting between the velocity and the distance. So the recessional velocity is a constant times distance, and that constant is approximately 70 kilometers per second per megaparsec. And so now you can actually use the recessional velocity to measure the distance, more or less, although we'll come back to when that breaks down next week. So what does that mean? Well, here I have an animation which will hopefully play itself nicely. Here we go. So here I have a set of galaxies. So I've got galaxy A, B, C, D, E, and they're all equally distant. They're on this grid. So each of these grid references is the same size, and so they're all the same distance. So A and E and A and B are the same distance, B and C are the same distance, C and D are the same distance. So you've got this set up like that. Now, what does it look like as the universe expands from the point of view of someone standing on galaxy B? Well, we can see that we went from being 100 to 150 parsecs away here. This one went from 100 to 150 parsecs. But this one went the square root of 300 parsecs. And this one went even more. This one is now 300 parsecs away. So depending on the distance away they were in the first place, they've now got even further away. And so this means that you've got the same Hubble law applying. We're going to watch this again from another perspective. So the universe is going to look the same regardless of which galaxy you're sitting on, because it's the space that's moving, not the galaxies. Okay? Man, this is slow. Keep going. There we go. Okay, so we're back here. Each of those squares is 100 megaparsecs apart, and as the space expands, from the point of view of A, you're going to have that B and E both get to 150, but C is now twice that, 300, and D is now 450. So you get that increase in movement away as you get further away from the original point. And that's where we get the origin of the expanding universe. Hubble's law is best explained by this. And the thing to remember is that the universe is expanding, space is expanding. It's not that the galaxies are moving through space, space itself is growing. And so Hubble's law is just a natural consequence of this particular physical aspect of the universe. And so, we've got this idea that the universe has been expanding, but that means that as we go back in time, the universe was smaller and the galaxies were closer together. And if you extrapolate that back far enough, eventually everything will be at the same single point. And this is where the idea of the Big Bang comes from. The Big Bang wasn't something that was theoretically invented by somebody. It was something that was put out there as a natural consequence of what we were seeing happening in the universe right now. And so if you take it backwards and assume that the expansion has been more or less constant, then the universe started a little under 14 billion years ago, and it would have been at one tiny point and it expanded outwards. And we're going to look at more details of that next week.